today will be unfortunately relatively dry, but I do want to do a real bit of just dropping some of basically a lot of definitions, but also trying to talk through some of the intuition of linear algebra, and then we'll get to the point where it connects to regression. But first, reminder, homework 1 is due on Friday. I don't think we ever talked about how we want to do homework submissions. I have the D2L Dropbox open for it, and that is one way that we could do it. I would like to agree that everyone does it the same way. The other option is for you to create an assignments or homeworks folder on your forks of the repo and commit it there on GitHub. I'm personally fine with either way. I think for this class, because there's going to be a mix of, reading and analysis, writing things, doing code, making figures and stuff, it's fairly heterogeneous. There's not really a preferred way for me. Okay, so let's maybe put it to about, I'll give you 30 seconds to think if you prefer D2L or on GitHub. Okay, votes for D2L. Votes for, maybe I should say votes for don't care. Okay, and then votes preference for GitHub. Got 2, okay. Most people don't care. GitHub is a good skill to learn, so I'm gonna go with that. So if you need help with that, please talk to me. If you can't figure it out,
how we can get the notification for the deadline, or if you have a homework?
The deadlines will always be, let's just always set them to Fridays at midnight.
Okay, and we will have homework every week?
No, probably not.
Okay, how we should?
Maybe every other week.
Okay.
Yeah, how do you want me to
because in detail we can see we have homework or not, but in the Git, I don't know how.
I can still create the
Create an empty one.
Yeah, I can create the assignments on D2L even if you don't submit there. That also lets me enter grades, which doesn't really affect anything, but then you can see it more easily. Because I'll submit your feedback. If you're going to submit on GitHub, I'll submit your feedback on GitHub directly. But if you want to see a running average of your scores or whatever, then I'll still enter them on D12 because it's just me entering a number. Does that sound good to everyone? If you have questions and if you're feeling like you can't figure it out for this first week, just shoot me an email or whatever. We'll figure it out.
And do we submit the homework in the main branch, or do we need to create a new one for them?
Yeah.
So make sure that when you do your homeworks, in this case, put them on your fork of the course materials and just create a homeworks folder or something like that and just put them in there. So then folder, subfolder for homework 1 and then all of your files, and then I'll be able to look at it. Were there any questions on the first homework? Has anyone not started it?
We have to pull it in.
Yes.
Okay.
I can show you where it is in a second. You can also just view it on the website or on the GitHub.
On the GitHub. Okay.
I don't think it shows up on the website yet. I should make it does. Okay, cool. Yeah, I didn't check that. So again, I just want to continue to reiterate this I'll probably put this in all of my slides. Just to make it easy for you, but I'll probably start putting it at the end. But again, all of the materials here. Let me pop open the website and see what we got. I don't think the assignments show up on the website directly. But they do show up. So again, the assignment 1 is there's going to be this assignments folder, and what I'm basically going to do is just for every assignment, there will just be a new markdown file. And so again, this one has that due date. And then, just the problem statements here. And then, you can do one file per question, or you can just do it all in one thing. I don't care how you submit it personally. If you want to submit it as a Jupyter notebook or a write-up or a PDF, whatever you want, just make sure that you have the questions. Any questions on the homework so far? Also,
I just can't find it in my.
Also, usually in the detail.
Oh, okay, cool.
did I put it on the D12?
I think so.
Okay.
You can try to go to the detail.
Yeah, Jack, if you go to the main course repo, you can find it there at least.
Yeah, for this one, also you're doing the digital. There is a link in the digital.
Okay, yeah, I'll try and do that for all of them.
Okay, gotcha.
Okay, you got it? Everyone can find homework one?
Yeah.
Okay, cool.
Yeah.
And last piece of bookkeeping. So last time we talked really high level about regression, how to think about like how we're actually assembling data. We didn't talk about any like technicalities of like how you do it or what the math behind it is, but really thinking more about how you arrange data. And then again, that video from Nathan Kutz that I posted, please watch that at some point. I think it makes over and underdetermined systems very intuitive. And today we'll talk about how to go from linear algebra to regression, and then we will start to pop into optimization on Friday, at least very rudimentary optimization. And then what we were supposed to do this week was the differential equations and more optimization stuff. So we'll do that next week. And then because we're a bit behind on the schedule, I was thinking about skipping the statistics refresher. Personally, I don't think it's super necessary for this class, and we can fit in the pieces where we need to in the other parts. Does anyone have a problem with that? Essentially what we were going to cover is parameter estimation and maximum likelihood type stuff, and some basic definitions, but a lot of it doesn't factor in super deeply into what we'll need to do. And in fact, some of it is actually a little bit counterproductive in a certain way for what will come later in the semester. But so then in 2 weeks, we can just jump straight to the singular value decomposition, which will be a total left turn from ODEs and stuff that we'll talk about next week. But we'll figure out sequencing at some point. So is everyone okay with that? Does anyone have like a super burning desire to catch up on stats? No. Cool. All right, then we can just, yeah, we can jump into this. I do want to just note one thing. I'm going to assume for all of our work here, we're going to be working within sets of real numbers. All of this has theory for complex numbers, but because we aren't going to use them, it just makes some of the definitions a little bit more cumbersome. And realistically, for those of you who care about this stuff, there are certain spots where basically you just have to, for going from real numbers to complex numbers, you just have to change the transpose to complex conjugation. And if you don't know what that is, that's fine. But just to say, if you see this in like a textbook and they have it written out for complex numbers, which is the more general case, the notation will be a bit different, but complex conjugation for real numbers is just a transpose. So that's fine. Okay, so getting straight into it, I have some dry and boring things that we need to talk about just so that we have a set language, and this will help us when we're thinking about what happens when we have higher dimensional spaces in the future. So I think it's worth having these definitions in language. So everything in linear algebra is a vector space, which we call V, and all it is a set of vectors, which can be either finite or infinite, that is closed under linear combinations of its elements. So this is the essence of linear algebra, right? We only have linear operations to work with. So a vector then is just an element within a vector space. So it's like an example of a thing that defines the vector space, or that is defined by the vector space. So an example of a vector space would be just all of the points within R to the n. So if you're talking about Euclidean space, you know, just your classic XY axis, any point within that would be, or the set of all points within that is the vector space, and a vector would be a, you know, a set of 2 numbers, right? And if you go to higher dimensions, it would be, you know, a set of 3 numbers, 4 numbers, etc. You can also have more complex things. So the set of all polynomials, which would be defined by, you know, the sum of coefficient times x to the power, that would be a vector space as well. You know, right? You can add together polynomials. You can subtract them, divide them, etc. You've all seen this before. And then an element of the polynomial vector space would just be any given polynomial. So x squared is an element of that vector space. So we talked about this a little bit, and it is slightly important to continue to consider, but the set of all vectors, or for a set of vectors, the set of all of the possible linear combinations of them is called the span. That's, again, for a linear model, that's like all of the points you can hit. So if your data is outside of the span, you have intrinsic error. So that's sort of what we would call model misspecification. So your system would have to be nonlinear in that case. Does that make sense? And for the most part, we are going to have error when we talk about linear models. And that'll come back at the very end here. The last thing that is worth talking about, and it will come back a little bit when we talk about PCA and extensions to it, and then also it will come back when we talk about regularization of higher dimensional models, this idea of a basis of a vector space. So this is the set of linearly independent vectors that span the entire vector space. So there are many unique representations of any given vector space. Some of them have this property of being a basis, which means that the set of vectors that span the vector space are all independent. This is sort of like the minimum description of a vector space. Does that make sense? Yep.
So this is like you have like a set of data, it's like the minimum amount of like orthogonal vectors you can make out of that data.
Yep.
Gotcha.
Yeah, exactly. So when I say linearly independent, that does mean they're going to end up being orthogonal, and I'll give that definition in a little bit if you haven't seen it, but it's boring. And so sort of, I think the thing that's important to think about with a basis is this idea that it's sort of like, it's not necessarily the simplest description, but it is sort of the one that maximizes information about each individual piece. And again, bases may not be unique. There can be multiple bases for certain vector spaces. And that kind of means that you have like equally descriptive sets of vectors that can describe anything within that vector space. Cool. Okay, so just having a vector space is not very fun. We want to be able to do something about it or do something with them. And ultimately what we want to use linear algebra to do is computation, right? We want to transform inputs and out to outputs. So if we have two vector spaces in, it should have been R to the n, but you know, just think of it as a set of real numbers. We have these two vector spaces. We can define this idea of a linear map, which basically is just a function, which if you take a linear combination of any two vectors from V, so again, X and Y here are from the input vector space. You can scale them and add them. And what you can do, if it's a linear map, it satisfies this property where you can factor it out to have the scalar values outside the function, and the function can be applied independently to the two vectors. That is all a linear map is. And what you can think about with a linear map, especially in Cartesian space, all a linear map is a stretching, a scaling, or a rotation. Those are like the three operations that you can do with a linear map in two space. Right. And similarly, like you could imagine in three space, there's also a set of operations you can do: scaling, stretching, sort of inverting. So like this is sort of the idea, like when you look in a mirror, why are you not flipped? You're actually like turned inside out, right? So that's sort of the other operation in three space. Okay, and the connection between linear algebra and regression here, that starts to, yeah. Jose, do you want to explain it?
I have a question. I can understand how to stretch the shape, how to represent the rotation.
Rotations would be like,
Depends at what space I think we are talking. For example, the shape can be like D or it can be like E.
I don't quite know what you're getting at. So,
I think maybe if two matrices multiply, one matrix multiplied by one matrix, it can stretch the shape. How to do rotation forward.
Rotation would be signs within the matrix, right?
yeah,
And then so you have like the negatives, and it'll like take your vector and like flip it over and maybe stretch it or something.
Yeah, exactly.
yeah. So basically,
Changing the shape. Yeah.
if we're doing sort of this mapping, right? We want a function. So if we're doing this mapping here, so this is, let's say, -1, -1, and this is 1, 1. We want this to go to 1, 0, and this to go to -1, 0, right? So we want a function that satisfies the property of f of 1, 1. And like all you want to do is basically find a map that satisfies the constraints for these four pieces, and that actually was going to be one of your homework questions for the second one, was going to be to find the linear maps that actually do this. But it ends up being, scaling is just a map of scaling. So if you imagine, well, wait, I'm burying the lead here, so hold on 1 second. It turns out for any linear map, there exists a unique matrix that satisfies that function, which is just a matrix equation, right? So that's like sort of the connection between linear algebra and functional, thinking about things as functions. So before we talk about rotations, let's just do a simple scale. So I wish I had more space than this. Thank you. This should be fine. So if my function is, right, we all know what this matrix is, right? The identity matrix. What does this do? If I have a unit square as my input, let's say. Yeah. Okay, so that's going to expand it. What about? Yeah, it'll stretch it in the x dimension. Yeah, and I'm saying this is like, I don't know why, sort of. Okay. I mean, you can imagine what this one is going to do as well. Yeah, it's just gonna take every point and map it to its negative. Okay, so it's when you start getting cross terms that you start, so like, let's say, right. We can calculate this out. If you have 1, 1 here, easy enough, it's right.
One.
Right, you can just
One.
do this out, yeah. Okay, but then what happens if we start to swap things out?
Zero point five.
It's probably
0.5.
Okay,
Yeah.
yes, then. Yes.
So that would map us sort of, this shrinking again. So I encourage you to sort of work these out, and you can start to see how the matrices in 2-space start to let you do this. The one thing that you'll note is if you apply a linear transformation, you always, any segment that is linear on your inputs will always be linear on your outputs. So you can't have things where you kind of create curvature, more or less, or you can't modify curvature. If your input had curvature, you would still preserve that, right? Like if your input's a circle, you still get a circle or an ellipse out, right? But you can't get something that turns into a sharp edge. That's the main thing that you need to be aware of. Okay, so when we talk about measuring vectors and matrices, there are 2 things that we need to talk about. And that is inner product spaces, and we'll talk about norms in a second. Okay, so inner products are really very simple. The inner product of 2 vectors, which I actually probably should have had. Inner products are usually specified by some vector u and v, and they have some output to them. But they have these 3 properties. So this, you can think of, this is a vector, right? Right, we've already defined that. Anything that's a linear combination of vectors is also a vector that you can't get outside of your vector space. So this is a vector and this is a vector. So the thing that's important about this is you kind of have this distributive property where you can take the linear combination and factor it out, where you apply this part first. So we take a or a u, and then with w, and same with v and the v. This is one where, again, that complex thing comes up, but basically if you take the inner product of a vector or 2 vectors, you can swap their order and do the transpose of it. You can kind of think about this as if you swap the order, all you have to do is swap the rows and columns, right? And then the inner product of a vector, or of a vector with itself, is always 0 unless that vector is itself 0. And that's just a nice property that that lets you do some calculations of length and things.
The inner product of 2 vectors is a scalar.
Yes.
Where scalar has transpose. Maybe it has, but
Maybe if you go with matrices and you have matrix spaces.
Yes, yeah, that's the, yeah, exactly. Thank you.
Matrix spaces. So.
Yeah, vector spaces don't have to, like, vectors don't.
Values don't have to just be vectors.
No, they don't have to.
Okay. And then the last part that's important is, this is really the key thing that you need to know about inner products, is they define orthogonality. So if 2 vectors are orthogonal, their inner product is 0. And that just means that, yeah. they're essentially for like two space, this just means that they are perpendicular, right? And this is what will define independence later when we talk about that. The last piece of measuring things is the vector norm, which is a map from a vector to a number. Oh, my formatting didn't quite work. And it has these properties. So the norm of a vector is always greater than or equal to 0, and it's only 0 if the vector is the 0 vector. Again, that is just a nice property that lets us ensure some constraints. The scaling, so I probably should have made this bold or whatever. Alpha is a scalar value and B is a vector. You can factor out the scalar value, but you have to take its absolute value. Again, it should be obvious why you have to do that given this property, right? And then we have sort of this triangle inequality as well. The norm of the sum of vectors is less than or equal to the sum of the norms of vectors, right? That kind of makes sense. Yeah, this is just triangle inequality. And then the most important norm that generally is used in data-driven modeling is called the P norm, and it is, denoted with this subscript P, and it is just the sum over each component of the vector, where you take each component, its absolute value, again, due to this, and raise it to the power P, and then once you're done, you take the P root of it, right? You all have seen this before. If you think about sort of geometric interpretation of these P norms, this is what they look like. So there's a couple things to note. For the one norm, you get this diamond shape. The two norm is your classic unit circle. And as you go up and up, you get these sort of more sharper things. And then the infinite norm is a square. The last thing that you can note is you can take norms of matrices, and that again defines different shapes. So at this point, you should be thinking some things, right? That this should start to connect with things that that you've seen from regression before, right? Is anyone starting to see connection? What if I ask you about measurements of distance?
That'd be your norm between 2 points.
Uh-huh.
Okay.
Norm between 2 points is a measure of distance. So this is just defining the P norm on the unit circle. But if you start to think about norms of combinations of vectors, or if you have like an error function, that will have a norm to it.
Or like if you have data in your model and then you're trying to like do the difference between your model and the data or something.
Uh-huh. So if you think about these as distance metrics, some of these have special names. This is known as the like commonly referred to as like a Manhattan distance, and it's called Manhattan because it's like a grid, right? The only points that you can reach on it are following a grid, sort of like city blocks. This guy here is known as like a Euclidean distance, or something that you might calculate if you're doing a regression or machine learning model. Anyone guess what it is or think about what it might look like?
Hazard guess.
Please do.
I think it would be like a two-dimensional representation, because like I've worked with Euclidean normalization,
Mhm.
and at least conceptually, it's kind of the Pythagorean theorem,
Mhm.
and then you're projecting that back from a higher dimension down.
So if we think about, let's write out the equation for the 2 norm then. So We're going to write. Yeah, I hear it being whispered. It's. Right. So if U is actually like your errors in your model, you know, if it's x minus x of I minus y of I, then all this is right, it's just your mean square error. So if we think about that, then can I ask you what the one norm would be? Yep, mean absolute error. What about the infinite norm?
Max error from the view.
Square error. What is it?
I want you to think about it for a second.
Wouldn't it be the mean and
Oh, is it the log?
root error? I'm not sure how to
Log.
say it.
It's a little bit hard to think about, right?
Of the way of the.
Like if I write the equation out,
Like, you know what it is? I don't know how to put it in words.
Yes, I'm thinking about the.
I think I can see it in my mind.
I forgot the.
It's in my mind.
Because
Be able to show
usually
you.
it's the infinite, the limit of the something raised to 1 over something power.
yeah, how does that work, right?
Yeah.
It's crazy. Yeah, you'd have to take limits. You can maybe more conceptually think about it this way.
I'm sorry, I'm not understanding this figure much. So we have something like this, and then we take its infinite norm, and then it moves it like this.
So again, it's on the unit circle.
Okay.
Maybe I can draw this out because I think this is worth thinking about. That's a decent circle. I've been worse in my life. Okay, so it kind of puts it in a bounding box, right? It's right? It puts you on the boundaries. So for every point, it maps it to the most extreme value.
So is it just the max?
Yeah, it's just the maximum error. So if you're trying to, so the only thing you care about is reducing the worst case scenario, the infinite norm would be what you'd want to look at, but you don't care about anything else. So I think it's worth thinking about norms and stuff because, you know, I think for most problems we go, we'll do MAE or MSE, and it almost always works. But
Yeah, I think if you start thinking, like, for example, when you talk about MSC, we say that higher errors will be magnified more, and it's going to keep being magnified if you go to cube to the fourth power, maybe to take it all the way to infinity.
Yep.
It's just the one highest value that matters.
Yeah.
That makes sense to me.
also you brought up NSE, right? That is what you said, or no? Or did you say MS?
Oh, we're talking about MSC when we're talking about.
Okay, sorry. Yeah. Yeah, exactly. So I think it's just worth having, you know, trying to map this geometric interpretation to error modeling. He'll come back. Yeah. Okay, so as I said, you should start, and this is one of the things I really want you to get out of this class is you see a lot of these same concepts over and over, and the connections aren't necessarily often made. So for all practical purposes, regression optimization and the underlying theory of solving ODEs is numerically solving ODEs, not analytically. It's all the same stuff. It's all choosing an error metric, probably some p-norm, almost in most cases. Sometimes we add on other weird little bits, but usually that doesn't have a lot of theory associated with it. It's more of a feel, go by feel thing. And then you minimize that error using some optimization technique. And it's all the same, right? Okay, so going to regression and norms, if we have our nice linear system, AX equals B, for now we can assume some model structure, just a linear thing, of course. We could talk about other model structures that also have linear, like when we say linear regression, this is what we mean. But again, linear algebra and linear regression are sort of two separate things. Polynomial regression still falls under the case of linear, right? Because it forms a linear vector space. So I just poorly named, but here we are. So we're assuming a linear regression, which falls under the scope of linear algebra. And we want to fit it to some data. We want to find the best beta 1s and beta 2s that we can, given some data. Necessarily, we have noise, we have nonlinearity, we have all sorts of things. So the general structure that we come up with is the function for any given sample, x of k, any input from our data set, will have the property that it will satisfy the output that we're trying to get for that particular sample, plus some error term, right? Seems fairly reasonable. So then the entire field of regression is finding this, basically. So we want to find and this should probably have a subscript of A, and I probably should have changed B to Y. We just want to find the lowest amount of error that we can, given this F in our case. Again, F here was this linear model. It could be a polynomial model. It could be a nonlinear model too. But for the sake of everything that we can solve sort of in short term, we're going to be talking about linear systems. We'll go to nonlinear later, and you'll see why. Okay, so as I mentioned, the linear equation we can solve directly. Polynomial equations we can solve directly, and exponential systems we can solve directly. There may be some small other classes of functions or functional systems that you can solve directly and actually analytically find the min of this, but for the most part we can't. And most of our models don't look like this, right? Like a hydrologic model doesn't look like this. If you take like what am I trying to say? Sinusoids, you can't analytically solve for most systems. So then the next thing that we're going to talk about on Friday is how to sort of jump into optimization and how we use optimization techniques to solve these equations and fit models to data. Cool. That was all I had. We got 5 minutes out. I think this is the first time I didn't keep you more than 5. So.
Can we go back to the Spider-Man slide?
Yes.
That's a good slide to end on.
Okay, yeah, we can end that. Yes, and again, I think this is just one of those things that it wasn't until I learned deep learning that I was like, wait a second.
It's how do you say solving ODEs is similar to optimization?
That's what I'm wondering, because I feel like solving the ODEs, we did it with like the Euler methods,
Oh, that's baby stuff.
That's baby stuff? All right, cool.
Euler's method is so bad for ODE solving.
It works for my research. So.
Are you using forward Euler?
No, I'm using the implicit Euler, and then like Runge-Kutta and like all those as well.
Yeah, so I should say, what I really mean here is implicitly solving ODEs.
Okay,
Oh,
I gotcha.
that makes sense.
Yeah. Explicitly solving ODs still can have a little, it still does have some optimization if you do adaptive stepping. But if you use fixed step explicit methods, which we'll talk about very briefly, then there's no optimization. It's just the function is what it is.
In the root finding when you're doing implicit solving.
That's an optimization.
So for like backward Euler, that's an optimization problem.
Uh-huh. So here, yeah, if you're willing to stick with me for a second.
Yeah, I would love to.
This is trying to find the minimum distance that your parameters of your function give to reproduce data. If you want to
Oh, okay, I just got it. So it's like if you have your, implicit Euler, if you're doing like the step un and then un plus one or whatever, then you have your matrix that is scaling un to be n plus one, then you're going to just be minimizing. Okay, I got it.
Does everyone else kind of see where he's going? I'll draw that exact.
I just never thought of it like this.
Yeah, and that's what I want you to do.
Okay.
I want you to see that connection. So yes, and the other thing that I want to note is yes, in machine learning there are many classification techniques that we won't be talking about, and the ones that we will talk about are going to use deep learning methods. And deep learning is fundamentally a regression problem. And if you want to do classification, there's an extra step to it. But at the end of the day, it's mostly regression. Or at least you can think about what's happening as mostly regression. So, let's end it.